Okay, that should be this. All right, so just for your information, we will be, looks like we're working the technology to be able to record all the class sessions. So we'll be meeting here normally. Somebody kind of had a panic attack when did this in the other class, asking, wait a minute, we're not going to online, are we? Answer is no, we're not going to online. However, this is a convenient way to get the recording going. So, and to let you all know that it's there. So, what that means is even if you don't, oh, let's see, do you have to attend? There'll be a link. There'll be a link so that you can get the recording if you want to later down the road. So looks like we are going. So this is recorded. Okay, so the first step, continuing into our NFA discussion, is comparing the DFA versus the NFA. And there's the primary, well, you tell me, what is true about a DFA that is not true of an NFA?
DFAs only have one route per input.
Yeah, one arc per symbol, per alphabet symbol. And NFA can have, so our DFA must have one arc per symbol. You can't skip, and you can't have more than one. So it has to be exactly one. Whereas an NFA can have 0 or 1, 0 or more is what I meant. 0 or more per symbol. Anything else?
NFA is going to include the note, the empty check.
Yeah. An empty string is a thing that, and it's in an NFA on an arc. What it does is it causes a spontaneous move without input. So it allows you on the DFA, a move requires input. So the DFA is, well, very deterministic. It's very easy. There are no choices involved as it goes along, right? And so it also, it reads a character, makes a move. Reads a character, makes a move. Continues on that. There's never any choice, and it always has a move for each symbol. So its whole processing is Look at the symbol, move. Look at the symbol, move. Look at the symbol, move. When it runs out of symbol, it says, where am I? And then if I'm in an accept state, accept. If I'm not in an accept state, then reject. All right, so it's very mechanical, I guess. In a sense, the NFA is also mechanical and is going to move through, but it has a few options on how it's going to process and how it's going to move through the input. So it'll still move sequentially, left to right through the input, but it may change states, and it may actually, the easiest way to think about implementing it is it may occupy multiple states at the same time. So a DFA is always in one state at all times. NFA may have multiple states, and usually say it had multiple states activated. I said there are a couple of different ways of thinking about the NFA and how it non-deterministically moves. We know that if an accept path exists, the NFA will find it. I guess we could say as will the DFA. What about how they accept? The DFA at the end of the input, check the state. Check state and stop. So checking the state means figure out whether you accept it or not. What about the NFA? What does the NFA have to do? There is a condition. You have to, it is possible for the NFA to stop without using up the input. How would it do that? If there's no path on the current input, in other words, if I had just had an NFA that had this, and I feed it so this is an NFA. It has no arcs coming out of the accept state. And what would you describe? What is the language accepted by this NFA?
Except that one.
And more specifically?
If there's at least one. Well, a number of zeros and then adding in a 1.
Yeah, any number of zeros, right? You have to put that part in, including 0, and ending in a 1. So now strings that just have a 1 in them, we need a different NFA. This one is right. So we want to be as precise as we can be when we're talking about what does it accept or not accept? Build one that says, build an NFA. Where you are. Pop quiz that you don't have to turn in. Just getting a little adrenaline flowing here. Try to create an NFA to accept L1 strings over A, B, having 1A. Okay, so we kind of have some things implied there. The alphabet is A, comma B, and we're saying we have exactly one A. Now, do we know whether it's at the end? It doesn't say whether that it has to be at the end or the beginning or in the middle. So we have to make it accept in any of those, right? So I'm trying to get to be careful that you don't either over limit and read too much into it, more restriction, or not enough restriction, right? I mean, so we have to kind of turn it around a little bit and make sure that we have both the everything that should be in there and everything that shouldn't be in there. One way to do that might be to list some good strings. Well, you know, A followed by any number of B's, the B on either side, the B's followed by an A. So those are all possibilities, right? We don't care where the A is. And bad would be more than anything that has any number of A's, or right. So just to kind of get a sense of what is it that we have to accept and what do we have to reject. So if we do an NFA, we can add, or let's finish the table here, and then you will have a nice answer for me. So so the condition to accept is a little more exacting for the NFA. We accept only if input used up because you might not use up the input with an NFA, because if there's no path to go, you never need a dead state with the NFA. So if there's no path to go, it just stops and says, can't go any further. There's still input, doesn't matter, I reject. So accepts only if input is used up, may stop before that. Because this always has a path to the NFA if no path to continue. And you have to be in an accept state, right? So it accepts only if the input is used up and you're in accept state. but it may stop before the input is used up if there's no path. But NFAs are a little bit simpler to create in some cases because of that elimination, you don't have to do a null or dead state. Question in the back corner? Yeah.
So even if it is currently in an accept state, if it doesn't have a path to go, and there's still input left, then it will fail.
Yes.
Even if it is at the time failing in an accept.
Yes. Yeah, exactly. And we'll look at an example here with this little guy. What would we do to get it string over AB having exactly one A in it? So it should accept every single string that you could possibly create using A's and B's if they have just one A in them. Somebody have a solution you'd like to suggest? We can make it an NFA. I assume you have a start state. Well, presume that Q0 is the start. So what do we do? What's a transition? Okay, B is looping. And
a Q1 state that is led to by an A.
okay, we can get there with an A.
That accept state is a
I'll
Q1.
make that accept.
Q1 loops on B.
Okay. Are we done? What do we think?
You need another node if there's another A, like a null state.
With an NFA, we
You
don't.
don't need the null state? Okay.
That's the difference. If this were DFA, you're exactly right that we would need a something to do on an A. When we don't have anything, it says you can't do anything. I mean, so the DFA would keep running until the end of the input by having a null state that just loops on itself. The NFA just comes to a screeching halt. You try to feed it another A, it just goes, can't do. The A is at least the A wherever we found that second A is left over with whatever follows it in the input, and it stops, and we are just.
So does it stop whenever it gets something it doesn't have like a description
Yes.
for? Okay.
Yep. It'll stop if it may stop if there's no path to continue. What do we think? We'll use this as a simple example to create a DFA using a little algorithm. Because it's a pretty trivial change, but it'll give, should go through the steps and we'll give an example. So what would happen if we fed it, if we have an input, this input AA, BBB, it's going to start here in the start state, and it will look at that and say, I've got one transition to make, so I'll go to Q1. And now it's in Q1, and it's going to look at the next input and go,
Stop.
can't do anything.
Stop.
Yep. Put on the brakes. And even though, right, so there's two pieces. Even though I'm in the accept state, I have to use up the input and be in the accept state at the same point. So the input's used up and I'm in an accept state. But this one, and you'll find that it's often easier. We'll use the NFA, especially with some epsilon moves, to make some to prove some points about regular languages and some of the closure. Right, closure means in this case when you are, if you have a regular language, and I think we talked about before, you take a regular language and you union it with a regular language, you get what? Regular language. So we would say that regular languages are closed under the union operation. Also concatenation, and also which is taking what, if you have two regular languages A and B, and you take a string from one of them and a string from the other, and you build a new language consisting of all the strings of A followed by all the strings of B, that is also a regular language. So concatenation, union, and then closure is basically just looping around and repeating and saying, take the strings out of language L and take as many repetitions of the strings in there as you want, sticking them together, and picking and choosing any one of those elements repeatedly, and that's also closed. That's also a regular language. So we'll demonstrate that having the non-determinism and epsilon moves makes for an easy way to do some of the proofs and actually show that these features that show the closure features of regular languages. So with these differences, one might suspect reasonably that NFAs are more powerful than DFAs. That they're, well, DFAs, we have the equivalence with regular languages. We said every regular language has a corresponding DFA. Every DFA defines or accepts a regular language. So there's an equivalence. When we say regular language, we mean a language that can be accepted by a DFA. Now what about NFAs? Can they do more than a DFA? No, it turns out that in fact a DFA is just a specialized case of the NFA that doesn't have epsilon moves, which are optional, and happens to have one symbol, one arc per symbol. And so how do we know that that's true? Well, the proof is that we can convert any NFA to a DFA. So how do we, are DFAs and NFAs equivalent? Okay, there's almost always, it's kind of become a tradition to throw an exam question with a statement like, NFAs accept a broader class of languages because they have more computing power than DFAs. And that is patently false. But you'd be amazed. There will be 10% or so people who look at that and go, that seems so reasonable. Let's see, how many folks have had me as your tormentor in a previous class? Okay.
I'm having you in for another class.
At the same time, which is building on the experience. But so You know that I like, for true false questions, I like to have very reasonable statements that if you actually know the material, you will conclude that they are false, or so be aware, just right when you're trying to, better to study and learn the material than count on being able to figure out, that didn't quite sound right. Better if you know whether it's right or not. Thank you. Anyway, are they equivalent? Yes, indeed. And the way we know that is we can convert an NFA to a DFA.
Can we do the inverse?
Yeah, you really need to do the inverse, because it's already a subset.
Yeah, that's actually, that very question just popped up as something that someone is bound to sticky stuff in the podium. Do we ever go the other way? Let me think about that. In a real sense, all of the things that are true on the NFA side would also hold if you have a DFA. I mean, in other words, right? If you must have one, then that counts as 0 or more. So this would meet that requirement, right? These are optional. That's on empty string is optional. So if you don't have any epsilon strings, then you're still meet the definition of an NFA. You're in one state at all times. Well, that's a may have multiple states activated, but you could have one state activated all the time. So this meets that criteria. And at the end of the input, you check the state and stop. Well, this one would, if there is a path, it'll use up the input. So if you happen to be this is just a little nicer way to stop. You're guaranteed that there's always a path for every input character. So that falls into this too. So a DFA is a special case of an NFA. So as far as power, they are equivalent. And to kind of prove that is the conversion process. Let's see. Yeah, this will be good first attempt. So we'll take this little simple NFA and just convert him over. The process is for each state of the NFA, start at the start state and create a start state for your DFA. And then the next state for each symbol, I have a handout for you, so you can follow along, jot the idea, but I also have it written down for you. So, and I'll, it's not just that I have it, but I will also post it. So from that initial state, for each symbol in the alphabet, figure out where the NFA can go. If it can't go anywhere on that symbol, create a new state that's a null state that loops on itself and make a transition on that symbol. So it's like for each, starting from a start state, for each symbol in the alphabet, figure out what state or states the NFA could be in, and make a new state representing either the single or multiple states that the NFA would occupy. So on a B, it just goes back, or let's start with A. On A, it just goes to Q1. That's pretty easy. So this is a simple example. We'll move up to another one here in a minute. On B, it loops on itself. And now for any new states that you've added that don't have all the symbols for all the arcs for all the symbols, pick one of those and start filling it in. So at Q1, we can, on an A, there's nothing. That means it goes to an empty set, or the null state. And this is on all symbols. The alphabet loops back on itself. So Q1 on an A goes nowhere. And Q1 on a B just goes back to Q1. And check each state that you have so far. Does it have transitions on every alphabet symbol? If so, you are done. There's a little, for epsilon strings, we have to do a little extra looking, but short of having those laying around, no epsilon strings, we just feel like so. Okay, so this was not in more than one state at any moment. We would run into that if we had multiple occurrences. So simplest, no multiple transitions and no epsilon moves. So next step would be, let's do one with multiple moves and see where that takes us. Okay, so I think we got. Let's leave that up for a little bit in case we need it. I'm going to take this guy out. Okay, NFA, let's just start with the NFA. Then we'll figure out what it accepts. Let's say we've got zeros and ones, and and with then we left out the copy of the anything that contains an accept state from the original has to have an accept. So I want this to go and let's make it got a couple of multiples here going on, so this should be complicated enough. So what would you say this accepts. Notice some of these may not be the minimal possible NFA or DFA that you could possibly come up with. But what about this one? Can you describe it?
Starts with a 0. Right?
Yeah, we gotta be.
There needs to be at least 1 0.
It doesn't.
Let's have at least a 0 and end with a 1. But it can have any 0s and 1s at the front before it gets there.
Not necessarily.
Oh, wait a minute.
Yeah, we can do 0s and 1s. Stay here as long as we want, right? And then
Oh, right.
jump on a 0, at least a 0, and then a series ending in a series of 1 or more 1s. Okay. Something like that. Okay, but notice we got a couple of different things going on. We've got 2 different choices happening. Here you got a 0 to decide. So how would it accept? Let's just look at it functioning for a moment. If we gave it okay, let's try this. What would it do? I'm gonna get my little red marker out. So what does it do when it sees 0? It's going to activate. It's gonna start here. It's gonna loop on 0 and also take a trip over here on 0. So it's going to. We can think of it practically as having multiple states as possible current states that could have a transition on it. So we then see the 1. Well, on the 1, it can loop back and this stays active. And on the 1, oops, it can loop back on itself, keep that active, and it can activate this. So by the time it gets to the second symbol, it can have 3 states that it could possibly be in at the same time. This is where the idea that it's going to find, well, what are some ways to think about it, right? It has all 3 states active, and if one of those, it's like having all the paths that are possible active and ready to try the next symbol. When it gets to something where I can't move on this symbol, then that whole path dies off, and it only has the other successful so far paths that could operate, that could function. Okay, so does everybody see why these 3 states would be active on just seeing the 0 and the 1? It would take, it's like trying every possible transition from where it is right now to where it could go. Yeah.
So if we like begin with 1, then it would just activate Q1, Q0 because we haven't
Yes.
activated Q0.
If you only saw, yes, if you only saw the 1 first, if you didn't have the 0, then it would just go to 1 and it would only have 1 state active. Good. Okay, so now I'm going to see next input character is the 0. And what does that do? Q2 on a 0 goes nowhere. So that path is unsuccessful, so that is no longer activated. If it's in Q1, it sees a 0. It can't go anywhere, so that one's no good. So what that's telling us is we shouldn't have gone down the routes, the alternate paths. We should have stayed in Q0, would have been the path to success, potential success. We don't know yet, right? So that 0 from Q0, I could loop on here. And that the fact that Q0 is already activated, this 0 can also come through and activate this guy again. So we had Q0 was on and waiting for input. We gave it a 0 and it said, oh, okay, I can loop by myself and I can go to Q1. So at the end of this character, it's a little maybe uncomfortable, but yeah, we just deactivated Q1 because when we were in Q1, if we saw a 0, it turned it back off because there's nothing to do. When we get finally back to Q0 and see the 0, it reactivates itself, looping back to itself, and the 0 turns back on Q1. All that's saying is you could go 0, 1, 0, right? Or you could go 0, 1, 0. So both Q1 and Q1 are possible states that we could be in at that point. Then we see another 0. When we see this 0, Q1 turns off because there's no place it can go. Q0 loops back on itself, stays active, and that second 0 can turn on Q1 as well. We're almost there. Q0 on a 1 can loop back on itself only, so it stays active. Q1 on a 1 can activate itself, and it can also activate Q2. And we've still got one symbol in input to check. Everybody good with that? We're tracing all the different paths. This Q0 being this input character on Q0, we could go 1 and loop back on myself, and I'd be here. Q1 on a 1 can loop back on itself and be here. And activate Q2. But the fact that Q2, so I probably, the first thing would be to check if anything gets turned off before we reactivate stuff, right? So sequentially, we'd say, well, 1, keep this guy alive, yes, and it can go here. Well, 1, keep this guy alive, no, there's no place he can go. So he would get turned off initially, and then when Q1 sees the 1, it can go there, activates itself, and also reactivates Q2. So we've gotten to the last of the input. Is this string accepted? Yeah, because one of the states that's active is Q2, and it's an accept state. And we used up all the input. Okay, no sleight of hand, no. Wait a minute, oh no, somebody coughed.
I can see how this helps with understanding NFAs, but will we ever have to track what states are active in an NFA like this? Or is this just an explanation?
This exercise is an explanation that is showing us how we will do the conversion to the DFA. So as an exercise, let's see. Will
we actually do this process of tracking?
You will do the process of creating the DFA.
Right.
But the tracking
Not exactly.
is on a one state at a time. So what we in the means the way we just did it, you probably would I would not have you go through that direction necessarily, right? So what we did is look at the input and specify all the states that would be activated each point along the way and what gets deactivated and all that. So that's not nearly as fun as going through and making a DFA out of it. And you're not being driven by the input side. So let's see what the conversion looks like. We're again going to start. My algorithm is a little bit simpler than the book algorithm on almost everything for construction. They take make the superset of all of the states. Remember what a superset is? It's the set of all the possible combinations of elements in a set. So like a superset, just quick example, if I had we'll do a simple one, the super set is the set of a set containing B and set containing AB. And if you had 3 elements, then it would be each of the sets that you could form by any combination of A, B, and say C. Right? So it gets quickly exponentially larger. So the book suggests making a superset of all the states. Your NFA has a set of states, and so we make the superset and enumerate all of them, all the possible combinations. Well, for a small, simple one like this, we did see that it could have Q0, 1, and 2 all activated at the same time, but that's not necessarily going to be the case. So a more direct, without having to do extra work, right? My approach is to start at the start state and only build the states that you need, the combined states that represent being in more than one state at the same time. Let's see if now. So there's a reason, there's purpose here for going through and showing the activation, because you could see the different states could be activated at the same time, and that's what where we have to build here. So start with the start state, and we're going to go for each symbol. So hopefully, we're walking through, talking through this. I will give you the handout with the algorithm, but rather than having just looking at that and going through it by rote, hopefully you get a little vision of why are we doing it, how are we doing it, and then when you look through it, it's like the algorithm will be more of a reminder than looking at this cold and trying to figure out what it's doing. Okay, so we're going to go through the symbols. We have to go through 0 and 1 for each state and go to the right place. So on a 0, where can Q0 go to?
Q1.
And Q0. So we need a combined state here representing the fact that on a 0, these 2 states are going to get activated, Q0 and Q1. Okay, and on a 1, where does Q0 go to? Goes back to itself. So we're 1 down, and we don't know quite how many to go. It depends on how many combinations there are. Right? Order does not matter. Q0, Q1 is the same as Q1, Q0, so no, it's not every possible permutation, just the combinations. Right? So where can this combination of states go? It's the union. So that's bad. There. So from these two states, you can go to, on a given symbol, on you can go to the union of all reachable states. So we look at first, right, so because it's sets, we don't have duplicates, we don't have Q0, Q0, we don't have Q0, Q1, Q0, we don't have any combinations going on. We're just saying, okay, look at all the places Q0 can go on a 0, and that happens to be, what? Q0 and Q1. So on a 0, what should we do? Well, we just go to exactly these two states, except what about Q1? Can Q1 add anything? We're going to union together everywhere Q0 can go, which is Q0, Q1, and everywhere Q1 can go on a 0. On a 0, Q1 can't go anywhere, so that's an empty set. So the combination of everywhere that I could possibly get to from Q0 on a 0, plus everywhere I can get from Q1 on a 0 is Q0 and Q1. Here's where it gets a little divergent. Where can I go on a 1 from Q0? Q0 on a 1, yes, goes to itself. What about Q1 on a 1?
And Q2.
Right, so we have to take the union of both of those. So we have to take all the places I can get on Q1, Q0 on a 1, all the places I can get from Q0 on a 1, which is Q0, union with all the places I can get on Q1 on a 1, which is Q1, Q2. So that's going to give me a new set of places to go. This is Q0, Q1, Q2. You see where that came from? Yes. Okay. You're just sitting there going, I don't know where he's pulling this stuff out of the air. Rope a hand and I'll show you the air that I pulled it out of. Okay, so it looks like we got two states done. He has a 0 and a 1 transition. He has a 0 and a 1 transition. It looks like we could be getting near the end. Let's start with 0. So if you're in all three of those states, Q0, Q1, and Q2, what are all the places you can go on a 0?
0.
Q0 will take me to Q0 and Q1, so I can start listing them here. Q0, Q1. If I'm in Q1 on a 0, I don't get any further. If I'm in Q2 on a 0, I don't get any further. So I've already got something, yay! So a 0 can take me back to Q0, Q1. We're just enumerating everywhere you can go with both of those states activated. Where else can I go? Or with all three of these states activated, where can I go? On a 0, I can go back to Q0 and Q1. Meaning, basically the Q2 path drops off. Now what about a, I need one more transition here. On a 1, Q0, I know takes me to just Q0. Q1 on a 1 takes me to Q1. Q2 on a 1 takes me nowhere. So where should a 1 take me here?
No?
Q0, Q1, back. Or Q2, so on and so on.
Careful.
One will, from Q1
Yeah.
will go to Q2.
Yeah.
So itself, right?
Yep. So we're not adding anything off of the Q2, but Q0 on the 1 goes Q0, so we've still got that. So we're enumerating them, Q0. Q1 on a 1 goes to Q1, and Q2. And so it loops back on itself here. All right, do we have any states that don't have two transitions, one for 0 and one for 1? Everybody's good, right? Everybody's got two transitions, so that means we're done. So notice we don't have a Q1, Q2, although conceivably, I mean, off the diagram, you might speculate that there could be a Q1, Q2. Turns out that's not actually possible. So we don't need Q1 by itself, Q2 by itself, right? The power set. So we don't have to do all of those guys. To be complete, we would create the entire power set and then check every single one and find out that most of those are unreachable. You just can't do that. By building it this way, starting from the start state, then you only hit the possible reachable combinations of states. So it's shorter. Now, where is the except state? Anytime you could be in Q2, then we should make our DFA have an except state. And it turns out to be fairly simple in this case. There's only one place, right? If we had a Q1, Q2, that would also be an except state. But as it turns out, we don't need that. We can't reach that where we only have Q1, Q2. So, do we think we're done? I think we're done. Now, do we think it's correct? Yeah. Confident. Well, let's see. Let's test. Does it accept this? Now we know exactly where to go, right? There's no picking whether to go. Where do we go on a 0? We start here. We go 0, 1. That looks like it would accept, right? That looks like the original. Followed by a 0. Okay, that'll take us here. We have to end in a 1. We know that in a series of 1s. We can have 0s, 1s, followed by a 0, any number of 1s, and we're done. So back to, we did 0, 1, 0, another 0 stays here. That 0, then a 1, another 1, and we end up in except states. So in general, the algorithm that he gives, probably partly because it's a proof, so showing that you're accounting for every possible combination of states, maybe that's more rigorous. For the proof purposes, to say, here's the algorithm to convert an NFA to a DFA, thus proving that an NFA accepts the same languages as a DFA. All right. So the next trick is simply taking into account empty strings. If you include empty string arcs, transitions, just add to the active states. So what we would do is find the epsilon closure. And epsilon closure equals all reachable states from where you are using epsilon. So if there is a, how can we modify this?
An empty string from Q1 to Q0 on, oh, no.
Let's see what that. What would that do? I'm debating whether to use one of the. There's a nice little. There we got it. Yeah, let's do this one from scratch. This is example 1.38 is the NFA. Let's see what that does. Recycle, reuse. We'll go 1 to Q. Oh, we're close. We go 0 epsilon. We take away this. We have a looping 0, 1, and a 1 takes you out. And then you have a 0 or epsilon here. And not quite there. And a 1 take you to the accept state. Oh, and then it loops on a 0, 1. Okay, so 4 states. Like I said, this is off page 54. Now, there's not an example of him, I don't think. See, does he convert that one? I don't think he converts this one. Oh, not I used the word superset. It was power set. What's the correct term here? Power set is what I just described. Okay. So I don't think he converts this one into a DFA. So we are on our own. Can you do it? Keep our start state. And what we just have to do is take into account the epsilon is, if I can get there and there's an epsilon out of it, I can also get to that one next to it and any epsilons that go out from there. So if there's another, if somehow Q1 is activated and there's an epsilon out of it and say another epsilon here, and I have to include Q1, I'm in Q1, plus an epsilon gets me to Q2, plus an epsilon gets me to Q3. That's the epsilon closure is how far can you possibly get using just epsilon moves from where you are? Which makes sense. I mean, it can get complicated and tedious, but the concept is just, if I'm here, epsilon moves mean I'm in all those other states that I could go from here as well. Just gets tricky when you're doing the union more than one. All right, so let's see if we can do this one. Q0 on 0. Looks like one choice. Okay. Q0 on 1. Let's be careful. Q0. Let's list them out. Q0 on 1. You can do it this way. Q0 on 1 goes back to Q0. It also takes me to Q1. And is there any way I can get further from Q1? Yeah, I can go to Q2 as well. That looks like the end of it, except yeah. So I just used up a single 1 can take me to both Q1 and by extension to Q2. And also Q0 loops back on itself. So my next state is all Q0, Q1, Q2 on a 1. Right? So Q0, Q1, Q2, that's kind of tricky on a 0. 0, where all can I go? Q0 on a 0 gets me Q0. I just write them down as I find them and then eliminate duplicates. Q1 on a 0 gets me Q2. Q2 on a 0 doesn't add anything. Q1 I'm not in, so I can't use the epsilon, doesn't do anything. Right, do you think this is it? So on a 0 from here, it's like we go to Q0, Q2. What about on 1? Q0 on a 1 gets Q0, Q1, Q0, Q1. But then with the epsilon, it also gets me Q2. Q1 on a 1 doesn't add anything, but the epsilon gets me Q2. And Q2 on the 1 can get me to Q3. New state. So on a 1, 2, 0, 1, 2, 3. We need them all. How about let's do Q0, Q2. This guy. Q0, Q2 on a 0. Q0 on 0 gets me Q0. Q2 on a 0 doesn't add anything to it. So you just go back to Q0. And we didn't add Q1, so there's no epsilon at all. So we get here.
Not 0.
Oh, yes. Thank you. Okay, and on 1, Q0 on a 1 gets me Q0, Q1. So we're including that. And by epsilon gets me Q2. When I get to Q1, I can also slip right over to Q2. And then Q2 on a 1 can get me to Q3. So notice that Q2 was from here, not, we didn't use an extra 1. In case we got to Q1, and then the epsilon would get the Q2, but the Q3 came from the fact that we were already in Q2 before we used the right there. Okay, so what does the 1 get me? To everything, right? Okay, now, maybe the last one, we can finish it up here. Q0, Q1, Q2, Q3, on 0. Q0, on 0 gets me Q0. Q, but nothing more. It doesn't get me Q1. So Q1 on a 0 gets me Q2, and the epsilon doesn't add anything to that. So Q1 on 0 got me to Q2. Q1 could have, if I was in Q1, I could epsilon to Q2, and then if there was a 0 there, I could go further, but not the case, so we just go back to Q0, Q2.
But doesn't Q3 loop in on itself? With 0 as well? On the.
Oh, I'm sorry, Q3.
Yeah, Q3 is
Yes.
still active.
Yep. Q3 is here. Q2 is 0, doesn't add anything, but Q3 adds Q3 in there. So we've got another Q0, Q.
But you're
That's supposed to be a 3.
stemming it from the wrong state.
Yeah, you're on.
Oops. He's already got this allocation. Here we go. 0, Q2. Okay, looks like we're there. And now the 1 off of Q0, Q1, Q2 on 1. We've got Q0, Q1. And Q2 gets us Q3, epsilon. Right, so all of them. Looks like it's 0, and a 1 to loop on itself. Finish this guy off, hopefully. Q0, Q2, Q3. Q0 and a 0 gets us 0. Q2 and 0 gets us nothing. Q3 and 0 gets us Q3. Oh my, it's going to go on. It's a 3. Okay.
If I may.
Left is an exercise to the reader. Yes.
Since in the NFA, Q3 is an accept state, and once you get to a state that has Q3 as part of it, it's impossible to get to a state that doesn't have Q3. Could you not just minimize your DFA by taking Q0, Q1, Q2, Q3, and just also looping itself on 0, since it always ends up at an accept state anyway?
In this specialized case, that looks self-evident, As far as an algorithm that will work all the time?
Oh, yes, of course, only in
Might
this case,
not.
not in this.
Yeah.
But in this specific case, I think you could save yourself a lot of trouble by just leaving 1 0 there as well.
But we have to be careful we don't jump to conclusions.
Also,
We'll finish this up last time. You might use that as an exercise. I think I got some more homework to post for you anyway, but you might look at that to finish it up for next time. I will, I'll give a solution for that.
Yeah.
One of those things that's just like,